So, now we have we need to use two programs. One is this, let me just clear this. So, if I do ls, so my relevant files are this one, which is my main program, and then this one, which is my the Fortran subroutine, which are the part of the LabPack subroutine which does the diagonalization. So, now remember, in order to compile this program, this particular subroutine, this dy dsy ev, this requires some other subroutines also. Let me see where it is written. Yeah. So, see, for example, here it requires this particular subroutine. Then if I go down, it will require another subroutine, and so on and so forth. So, these subroutines are part of the BLAS library. So, you need to have a pre-installed BLAS in your machine in order to compile this code, and the way the compilation is done is in the following way. So, again I am using gfortran as my compiler. So, let me just clear the screen. So, I am using gfortran as my, so gfortran is my compiler. So, I write gfortran minus o. The compiled output is stored in this file pw.val.x. Then the name of the main program which I want to compile, name of the subroutine which I will be using to diagonalize this matrix, and this particular subroutine needs to be linked to your BLAS library. So, that is done in the following way. So, minus L is the command, and then minus L, and then you have to tell where the compiler where this BLAS library is. So, in my machine it is stored in /user/local/lib, and then you link that particular. So, you go to that particular directory and then link the BLAS, and then you compile it. So, my compilation is done, and this is the output file it has produced where the executable is. Now, let us run this and see what we get. So, if I run it, so first of all it asks me for this parameters for this potential well, that is V 0 and B. So, let me choose V 0 to be 1 and my B to be 2. So, the depth of my potential is -1 and the width is 2. So, if we do that, so the code reads in and then prints out these values. Then it asks me the parameters for the plane waves, that is A, the periodicity, and N, which determines the number of plane waves. So, let me start with a small value of A, and let me start with say a small value of number of plane waves, that is 5 and 5. So, now if you see here, it does the job and then it prints out the lowest eigenvalues. So, let us look at the lowest eigenvalue, 3 eigenvalues. So, what you see is that the lowest eigenvalue is minus 0.52, then the next one is 1.19, and then the next one is 1.24. So, if you remember the potential which I am using, that is a attractive potential. So, we should have at least one bound state. So, and that is what. So, what from our solutions what we see is that we are getting one bound state, and then there are 2 unbound states here. So, now let us see how the values of these eigenvalues change if we increase the n, that is the number of plane waves. So, remember when I am choosing here n equals to 5 here, when I am giving an input n equals to 5, the number of plane waves is actually 11. Okay. So, let me keep the width, the periodicity to be of my plane waves to be same, but instead of 5, let me go to 10 say. So, n value I go to 10. So, what it means is that I have 21 plane waves now, and if I run my code, so you see the eigenvalues are changing. So, the new eigenvalues which I get is minus 5.521155, which is lower than this particular eigenvalue which I get when I use 11 plane waves here. If I reduce it, increase the number of plane waves further and do it, so then I see that my eigenvalue is the ground state, the lowest energy eigenvalue, it reduces further. And if I go to say 20, then you see there is still a slight reduction here. So, the question is this the correct behavior which we expect? So, to understand this, okay, but before we go to that question, so another thing which I have like to point out is that, see, for all the cases, the norm of the potential, norm of the wave function is always 1. It's approximately very close to 1. So, what I have done here is, okay, so now let us try to understand the behavior of my potential, behavior of my energy eigenvalues, that is these quantities here, as a function of the number of plane waves. So, I have taken this data and then plotted it, and let me just show you the result. Okay. So, what I have done is I have varied the number of plane waves starting from a value which is 11 to a value which is 51, and I have plotted the energy as a function of the number of plane waves. So, you see, as we go to higher and higher plane values of these plane waves, my energy goes down, and then gradually the differences between energies, say for example, in this case with 21 and 31, this difference is smaller than, say for example, 11 and 21, and as we go to higher and higher plane waves, this energy difference gradually goes down, it dies down. So, the question is, why are we getting this type of a behavior? Remember what the basic principles of quantum mechanics that we have used in order to develop this method. So, this is based on a variational principle. So, what variational principle says that the more and more number of wave functions you use in your expansion of the wave functions, that is more and more parameters you have, where my parameters are the coefficients, the closer and closer to the actual ground state you will go. So, what it means is that the energy, whatever energy eigenvalue I compute, or whatever energy of my system I compute, that will always be higher than the actual ground state energy. So, when you add more and more number of bases in your plane, in your wave function expansion, in this case we are doing a plane wave expansion of the wave function. So, you will slowly go towards the ground state, that means your energy will slowly, the total energy will slowly go down, and in the limit where it is converged, then you will not see any significant change in energy. So, that is why, as a function of the number of plane waves, if the code, if everything is correct, then you should always expect that your energy is energy should always go down. So, this is one thing, and then the second thing which we would also like to check is, how does the things change when you increase the periodicity of the plane wave. So, again I would, before we see the results, so I will just recollect what we have discussed regarding the periodicity of the plane waves. So, because we are using this plane waves and which has a finite periodicity, so what we have is, instead of just a single attractive square well potential, we have periodic replicas of that. Okay. So, what it means is that now I am not simulating or doing the calculations for potential which is 0 everywhere except between minus b by 2 to plus b by 2. Instead, I am doing calculations for a potential which has a non-zero value, say at around, so minus b by 2 to plus b by 2, and then again a non-zero value from minus b by 2 plus a to plus b by 2 plus a. Similarly, a non-zero value from minus b by 2 minus a to plus b by 2 plus b by a. So, these values, these potentials which are fictitious or potentials in our case, because actual potential has a non-zero value only between minus b by 2 and plus b by 2. So, so these are called periodic images. So, the correct picture. So, when I will the periodicity of my plane waves, that is this, if this A is only when the A is infinitely large, then only the distance between the periodic images and the actual potential, that will be large, and I will be simulating a correct the actual potential. So, therefore, it is important to understand how my results will change as a function of this A value, and what is a sufficiently large value of A. So, to do that, what I will do is I will now rerun the code by changing the values of A, that is this parameter, with a fixed value of the number of plane waves. So, since from that figure which we had drawn, which we had here, so we see that it roughly converges say between 41 and 45, things do not change much. So, what I will do is I will just run the code with varying the value of so, I will start with A equals to 5 and my number of plane waves n value of n to be 40, and I will just run the code. Okay. So, this is what I get for the eigenvalues. Now, what I will do is I will increase my A, say let me go from 5 to 10 the value of A, I keep the number of plane waves to be same, and then I run it again. So, what you see is, if you look at the energies now, the lowest the ground state energy. So, when my A is equal to 5, that means and if you compare that with the value when my A equals to 10. So, what has happened here is, when I go from this particular case to this particular case, the distance between the periodic images have increased. What it means is that now the interaction between the two square well potentials have reduced. Now, if you remember the potentials which we are using, these potentials are attractive potentials. So, when you bring two attractive potentials together, their interaction will also be attractive. So, when you move them apart, so what you will expect is that the energy eigenvalue, the energy will go higher up in energy. So, and that is what we find here. So, for 5 my energy is, for A equals to 5, my energy is 0.52177, but the moment I change A or increase A to 10, my energy goes to 0.456413. Now, if I change A further to 15, we will see that the energy goes much higher. So, now from 0.456 minus 0.456413, it goes to minus 0.453836. If I go to larger value, it will go even higher. So, actually what one needs to do is, one needs to systematically increase the value of A and see that at what value of A the energy does not change beyond a certain threshold. So, that value of A will be the correct value of A to describe my system within the periodic boundary conditions. So, let me show you a plot of that what happens. So, this plot shows the variation of the total of the ground state energy as a function of the periodicity of my plane wave, which is A here, and the number of plane waves I have used here is 51 in this for each of these calculations. So, as I was showing when running the code, so when I start with a small value of A, that means the potential, the actual potential is interacting with its periodic image and the ground state energy is lower. And then as I gradually increase the value of A, so from example, if I go from this point to this point to this point, so what is happening as I move towards the right, the separation between the potential and its periodic image is increasing, therefore, their interaction is decreasing, they do not see each other much, and as a result the energy goes high, and then beyond a certain value you see there is not a significant change in the energy as I increase A. So, a good choice of the value of A will be something around say 25 units here in this picture. So, now let us look into how my wave function look like. So, if I open the the output file which I have here, where I have stored my wave function. So, you see there are 4 columns here. So, the first column, this column contains the value of x, the position. This column contains the value of the probability density, and this column contains the real part of the wave function, and this column contains the imaginary part of the wave function. So, if I plot the same thing, so okay, let me just show you the plots. So, here what I have plotted in this figure is the real part of the wave function for 3 values of a. So, let us see with along the as a function of x here. Now, this vertical lines here, okay, I am sorry, this should be the vertical lines should be here at x equals to, this vertical lines should be at x equals to 1, because my total b is 2, and my wave the potential is symmetric from minus b by 2 to plus b by 2. So, these vertical lines here actually should be at 1. Let me just see if I can correct it. Okay. So, this is the same potential, the actual raw data. So, but before that, let me just double check the code what we have done. Yeah, it should be minus 1 to plus 1. So, what one should do is basically, let me just quickly modify this. So, this will be minus 1, except this will be plus 1, and okay. So, let me just print it again. So, let us see if the file has been created. Yeah. So, what we can do is, let me just go back and no. Let me close it and open it again. Okay, this is fine. So, as I was saying, so this vertical lines here denotes the width of my potential. So, the total width of my potential is 2, that is the value of b is, so this is the value of b, which is 2 units, and it goes from minus 1 to plus 1. Now, I have plotted here the wave function. This is the real part of the wave function, the imaginary part is 0 in this case, as a function of the periodicity of the plane waves which we are using. So, for 3 values of that. So, a equals to 5, 10 and 15. So, what you see for a equals to 5, your wave function is significantly different from that of a equals to 10 and 15, which are this blue and the green lines here. So, so what you see is that the wave function has not decayed by the time it reaches from the end of the periodic box. So, here my box, the total value of a is 5. So, it goes from minus 2.5 to plus 2.5, but as I gradually increase the value of a, so you see that it is going slowly going down to 0, and not only that. So, if you remember, my wave function should go exponentially to 0, okay, if in the actual case. So, if you look at the now the slopes of the wave function corresponding to a equals to 5 and a equals to 10 and a equals to 15. So, you see that A equals to 10 and 15, the slope in this region outside the outside my potential, that is on the left hand side of x equals to -1 or on the right hand side of x equals to +1, the wave function decays much faster. So, if I use a larger box, so I will expect it to go in a much quicker way to the 0. So, this is something one should be careful of. And another question is, so if we look into the results as a function of the A, so why does the energy goes up? So, the reason the energy goes up here is because I am reducing the interaction between the periodic images and my wave function is attractive potential. If my wave function is a repulsive potential, then what I would see is that the energy will come down as I move the as I increase the separation between the wave functions of between the actual potential and its periodic images. So, this is an example of how you can solve numerically the problem, the Schrodinger equation corresponding to a given attractive potential here in this particular case, and that attractive potential happens to be a square well potential with a finite depth. How you can use the matrix formulation of quantum mechanics and then convert your Schrodinger convert your problem of solving the Schrodinger equation, which is a problem of solving a second order differential equation, to a linear algebra problem, and then diagonalize that and then get the eigen values and the eigen functions corresponding to the ground state. So, though in this example, I mean, and in this lecture we have discussed only about plane waves, but there is no necessity that it has to be plane wave. This method also applies for the case when you use, for example, a localized basis set. For example, if you use atomic orbitals to solve your Schrodinger equation. So, then also this method applies equally well. In that sense, this method is a much more general method. Okay.